In this video, we're going to talk about elasticity. And so when we get to elasticity, we're interested in how objects respond to different stresses and strains. So up until now, we've had things like springs which stretch. But if we want to look at objects like pieces of metal and how they respond to forces, we need to look at stresses and strains. So stress is the amount of force per unit area that is associated with stretching, squeezing, or twisting. Okay, so now we have objects that don't want to be deformed, and we're applying forces to some cross-sectional area. And then when we do that, that's going to produce some strain. So you start pushing on a metal rod, it's going to be strained. And this is a measure of the deformation, so how much it deforms in response to that stress. Okay? And this is going to turn out to be a unitless quantity. Okay, so it's kind of like a length divided by a length. So if you imagine we have a rod and we're applying some forces on either end, say we're putting it in tension and trying to stretch it, then we're applying forces to this cross-sectional area, and that's going to cause it to change its length very slightly. Okay, so this is our cross-sectional area. Okay, and when we apply forces to areas, this is really a pressure. Okay, so a tensile, so you put it in tension, pulling it away, trying to stretch it, or compressive, meaning you put it in compression, or you're trying to shrink it, trying to compress it together. Tensile or compressive stresses are given by the equation F perpendicular, so perpendicular to the cross-sectional area, divided by that cross-sectional area. Okay, and then this has units of pressure, which we measure in pascals. Okay, so PA, which stands for pascals. Okay, so a force per area is a pressure, and then the strain that's produced, so the tensile or compressive strain, or the response to this, so what happens when you apply this pressure, you get a strain that is given by the change in length, so how much did you stretch it, delta L, divided by the original length, so L naught, how long did you start with. And so we're going to assume, if you imagine cutting this rod, when you pull on it on one end, and then you look at it inside, we're going to assume that this tension or this force that we're applying is going to be applied kind of uniformly. Okay, so it's in tension, so every direction is being pulled away. The molecules are being pulled away from the other molecules in the material. So we're going to assume that this is a uniformly distributed force, so a uniform force. Okay, so when we apply stresses and get an object to, or a material to stretch its length, we use what's called Young's modulus. Okay, and this is given by the variable y, so capital Y, and this is just the tensile or compressive stresses divided by the tensile or compressive strains. So this is the ratio of the stress to strain. So we plug that in, we get our force per unit area divided by delta L over L naught, so our change in length over our original length. Okay, so if we were to move this around to make it a little neater, our L naught's going to come up on top, our A will go down, and then we get our force divided by delta L. So sometimes it's written like this. And this, because our strain is unitless, that means this is still, we're dividing a pressure by a unitless number, so this will have units of pressure. So our Young's modulus is measured in pascals. This is our cross-sectional area. And this is our undeformed length. So whatever length we started with, F is the amount of force we applied, and delta L is how much the length changed. So Young's modulus is a property of a material. So it tells you how much, so property of a material. And it tells you the strain or the response of some material when some stress is applied. So for example, if you have a large Y, so a large Young's modulus, that means a large stress is needed to produce a given strain. So a large Young's modulus corresponds to something being hard to stretch, or it is very stiff. Okay, so a very stiff material. Okay, so you would have a Young's modulus for copper, a Young's modulus for steel, for brass, and so on. And so it's a property of material that tells you its response to certain stresses or pressures. So we said Young's modulus is kind of like a measure of how stiff an object is, or how much, how difficult it is to stretch it or deform it. And so you can kind of model it as a spring. If we look at Young's modulus, we have L naught over A times the force over delta L. And so what we can do is we can rewrite this in terms of the force, and we get the force is equal to Young's modulus times the cross-sectional area divided by L naught, the undeformed length, times delta L. And so what this looks like is F equals K times the displacement. Okay, so if you compared this to F equals Kx or minus Kx of a spring, then this is your displacement. And then the Young's modulus times the ratio of the area to the undeformed length, that plays the role of K, or your stiffness of that material. So we can also talk about the volume stress. Okay, so with Young's modulus, we've only talked about stretching perpendicular to some cross-sectional area of, say, like a rod. So it stretches in one dimension. But you can also have the same effect for the volume of an object. So if you imagine an object that is immersed in a fluid, fluids exert pressures on all surfaces of objects that are submerged in them. So you have, when you're underwater, you have water pushing on you from all sides. So all of you gets wet, not just certain pieces of you. Okay, and this pressure is kind of like a volume stress. So it's pushing on your entire volume from all directions. And that produces a volume strain. Okay, so you can imagine all of the water around you is pushing you, trying to shrink your volume. Okay, so you can imagine if you have some cube and it's submerged in water, it's going to have forces pushing on it from all directions, one from the back. And so it's effectively trying to squeeze it and make it smaller. So our volume strain would be equal to the change in volume over the original volume. So when this pressure or volume stress is applied, what that is a pressure change. So when pressure on an object changes, that is what produces, or that results in, a volume strain or a volume change. So a volume strain or volume change. So the way you should think about this is you always have air pushing on you. Air is a fluid. Just like being submerged, you're kind of always submerged in air. And so you always have these pressures pushing on you from all directions. If you increase or decrease that pressure, that air pressure, or if you submerge an object and another fluid's applying a pressure, that change in pressure is what's going to result in a volume change. And so to talk about this, rather than using Young's modulus, which is for a single dimension change, we have a bulk modulus. Okay, and we give this just the letter capital B, and it's given by the change in pressure over, so the volume stress over the change in volume divided by the initial volume. So this is the volume strain, but we also need a minus sign in front. Okay, and this minus sign ensures that B is positive, and the reason why we need it is because if we increase the pressure, so our delta P is positive, that's going to lead to a smaller volume. Okay, so if you push harder on something and increase the pressure, you're trying to compress it and make the volume smaller. So if delta P is positive, that means delta V will be negative, and we want our bulk modulus to be a positive number that represents how difficult it is to compress an object or a material. So the final type of stresses and strains we're going to look at is called shear stress. So a shearing stress, unlike the forces and the stresses that we saw with Young's modulus, it will be equal to the parallel or tangential forces with respect to some cross-sectional area. So in this case, F is tangent to some cross-sectional area, and that is called a shear force. Okay, and so we can now define shear strain to be the ratio of the displacement x to the transverse direction. So we'll see an example of this in just a second. The transverse direction h. Okay, so what does this mean? So let's say you have some rectangular prism, something like this, and it has some area, so it has some cross-sectional area on top, it has some height h, but then we apply some forces that are tangent to this area. Okay, so we apply a force this way that's tangent to this area. That's going to cause it to be deflected by some angle. So this might be some angle phi. So if we look at this triangle that's produced, we have this angle phi, and the object has been deformed, okay, or deflected some distance x corresponding to this angle phi. And so our shear strain, which is the response to this shear force, is just given by the ratio x over h, which, if this was given in terms of phi, would just be tangent of phi. Okay, so for this triangle, tangent of phi is opposite over adjacent, so that's x over h. And the reason why we write it this way is for x's that are much smaller than h, tangent of phi is roughly equal to phi. Okay, and this is measured in radians. Okay, and so this tends to be what happens when you shear some solid object. You apply some shearing force. it's going to change by a very, very small angle, maybe a few hundredths of a degree. And so this distance x is going to be very small relative to h. And so this angle is very small, and so we can just use phi in place of our shear strain. Then we have what's called a shear modulus. So for each of these different types of stresses and strains, we have a modulus. So the shear modulus is defined in the same way. It is the ratio of the shear stress, so the force per unit area, over the shear strain, so x over h. So we can write this as h over a times f tangent, or parallel to this cross-sectional area, over x. We can also write this, since x over h can just be approximated as phi. Okay, when x is very small relative to h, we can write this as f parallel over a divided by phi. Or you could write this as the force with your area on bottom times phi. So we're looking at all of these forces applied to objects that don't really stretch. So we don't think about forces on solid objects like we do forces on springs that cause them to stretch. However, there is a small region where we can treat these solid objects, these solid materials, as elastic. So if we plot the stress versus strain, so there is a linear relationship between the strain, how much it responds, or how much the length and volume change relative to their original length in response to some force. So if you apply force to a spring, it stretches linearly proportional to that amount of force. So for most materials, for many materials, they have an elastic region where the stress is proportional, or the strain is proportional to the stress, okay, or vice versa. And this is called the elastic region, okay, or the elastic response. Beyond this, objects will no longer act elastic. So they have some maximum point where they stop being elastic. So if you stretch a spring and you let it go, you know it will go back to equilibrium and look just like it did to start with. But eventually, if you stretched it too much, you would kind of stretch out the spring and deform it, and it wouldn't go back the way it was. The same thing with plastic. So if you stretch plastic very much, you know it's going to, it's not going to go back the way it was. And so once you pass this elastic stage, then you get to a plastic region where objects behave plastically. So if you stretch them too much or apply too much stress, they go into this region where they're no longer going to elastically return to their original state. And then past this, if you push it beyond this point, then you have what's called a fracture point. So this is when the object just breaks down. So this is the nonlinear region. So when it's elastic, it's linear. When it's plastic, it's nonlinear, behaves nonlinear. And this fracture point, where it occurs, is determined by what's called the tensile strength, or may also be called the breaking stress of a material. So both of these are properties of materials, just like Young's modulus, the bulk modulus, all of our moduli. And so plastic deformation would cause an object not to return to its original length. So it doesn't return to original length like an elastic object or like a spring would. So now let's sum up everything we've talked about. We had Young's modulus, which was given by variable y, and that was when length changes were caused due to a force that was perpendicular to some cross-sectional area. And then we looked at a bulk modulus, B, capital B, and these were volume changes due to some change in pressure. Okay, so we have some original pressure just from air. All fluids or all objects are in the presence of air, so they all feel some pressure, so we need some pressure change. So increase from 1 atmosphere, for example, which is what our air pressure is. And this has a negative sign out front because pressure increases cause volume decreases. So something to remember that's slightly different about the bulk modulus. And then for the final one, shear modulus, this is very similar to Young's modulus, but it is a deformation that is due to tangent forces, so parallel to the cross-sectional area rather than perpendicular, so due to F parallel. So now let's solve some problems where we go through and we calculate these properties of materials and use them to find responses to different stresses. So in this first problem, we have a wire that is 110 centimeters long and it is stretched to 112.2 centimeters by an attached weight of 250 newtons. If the wire has a cross-sectional area with a radius of 0.24 millimeters, find Young's modulus for the wire. So I'll start by writing everything we know. The unstretched length is 110 centimeters or 1.10 meters. Delta L, our change in length, would be 1.122 meters, so 112.2 centimeters, minus the original length, 1.1 meters, or 0.022 meters. Our force that's being applied is going to be 250 newtons. Okay, so you're stretching a wire, so you have some, this wire has some cross-sectional area and you're pulling on it, so I guess you're pulling on it from the bottom, okay, with a weight of 250 newtons. And then our radius is 0.24 millimeters, or 0.24 times 10 to the minus 3 meters. So if we write our equation for Young's modulus, this is the ratio of the force to the area times the undeformed length over the change in length. Okay, so I've just wrote it in a slightly different order. But we don't have the area, we only have the radius, so we need to write this as the force over pi r squared, since our cross-sectional area of wire is just a circle, times the original length over the change in length. And that gives us 250 newtons times 1.1 meter divided by pi times the radius squared, 0.24 times 10 to the minus 3 meters, times the change in length, or 0.022 meters. And that gives us a Young's modulus of 1.66 times 10 to the 7 pascals. Okay, so the first thing you notice is Young's modulus is a very big number, and in fact for many metals it gets even higher, so you should expect something times 10 to a very high power like 9, 10, 11, something like that. The next problem, we have a rope that is elongated by 0.9 meters after being pulled by the weight of a 50 kilogram mass. The rope is 52 meters long and has a radius of 0.4 centimeters. Find Young's modulus for the material of the rope. So again, this is going to be very similar. We have the perpendicular force per unit area times the undeformed length over the change in length. And so now we have a weight that's producing this force. So that's going to be mg times L naught. And again, our area, we don't have area, but we have a radius of our cross-sectional area. So this is pi r squared times delta L. And then we can just plug in. We have 50 kilograms times 9.8 meters per second squared. Our undeformed length is 52 meters. So it starts off at 52 meters long. And then we divide by pi times our radius, 0.04. And this is in centimeters, so times 10 to the minus 2 meters. And that needs to be squared. Times our change in length, so it was elongated, 0.9 meters. So that is our delta L. And that gives 2.25 times 10 to the 7th Pascal. The next problem, we want to find the minimum radius of copper wire needed if it is to be 2.5 meters long and stretch no more than 0.35 centimeters when pulled by a 420 Newton force. Okay, so we have some copper wire where a force is being applied. So our original length needs to be 2.5 meters long. We need it to stretch no more than delta L of 0.35 centimeters, which is 0.0035, or you could use scientific notation. The force that we're going to apply is going to be 420 newtons. And we could look up Young's modulus for copper, since it's a property of material, and it would be 1.1 times 10 to the 11th Pascal. So that's not something you should know, but something you should look up or would be given to you. And so now we look at the equation for Young's modulus, the force per unit area times L naught over delta L. And we want to find the radius, so instead of writing the area, we need to write it in terms of the radius, pi r squared times delta L. And now we can solve for the radius. Okay, so just move it up, divide by Young's modulus, take a square root. So we get F times L naught over pi times Young's modulus times delta L, and then we need to take a square root. So we plug all of that in. We get 420 newtons times 2.5 meters, the original length, over pi times Young's modulus, 1.1 times 10 to the 11th pascals. And the change in length that we want, 0.0035 meters. And that gives us a radius of 9.32 times 10 to the minus 4 meters, or 0.932 millimeters. The next problem, we want to know how fast can a 1,500 kilogram elevator accelerate if the steel cable has a 3.5 centimeter squared cross-sectional area and cannot exceed an elastic limit of 9 times 10 to the 7th pascals. So we have this cable, I'm going to draw it really big. There's some force being applied. Okay, and that force comes from the fact that it's supporting an elevator that has some weight. So if you do a free body diagram, this tension or this force in the cable is going to be to the weight of the elevator. Okay, so if you sum up the forces in the y direction, you get this perpendicular force minus the weight of the elevator is equal to mass times acceleration using Newton's second law. And so if we solve for acceleration, we divide by m and get the force divided by the mass. And then our masses will cancel here, so we just get minus g. So the next thing, we know the pressure is just force per unit area. And so this can be solved for the force just by multiplying by the cross-sectional area. So we get pressure times area. So now we can plug this in and we get PA over m minus g. And our pressure, this is the limit that the cable can take. Okay, so our acceleration is our pressure. Okay, so our elastic limit, 9 times 10 to the 7th pascals, times the cross-sectional area, 3.5 centimeters squared, but we need this in meters, so we need to convert it. So that's 1 meter for every 100 centimeters, and we need this to be squared. Okay, so we do our conversion factor and square it over 1,500 kilograms, And then we need to remember to subtract off 9.8 at the very end for G, so don't forget that. And this is going to equal 11.2 meters per second squared. So in this problem, it didn't tell us the maximum force that it could be applied, but it gave us the maximum pressure or the elastic limit that could be applied. And then we just used a definition or the definition of pressure to rewrite that in terms of the force. And then we were able to solve for acceleration using Newton's laws. In the last problem, we wanted to determine the magnitude of shear force needed to deform a brass cube with a length of 1 centimeter by an angle of 0.07 degrees. So our shear modulus is the stress over strain, which is F parallel over A, so our pressure, divided by X over H. And so again, we can write this as H over A times F parallel over X. But H over X, we said, for very small angles, which this qualifies as a very small angle. We can write this now as F parallel divided by the area times phi. Okay, so here we use the fact that tangent of phi is equal to X over H, but when X is very small relative to H, so very small values of phi, tan phi is roughly equal to phi. Okay, so this is a small angle approximation. And we don't know the area, we only know the length of the cube, but since it is a cube, that means that the area is just the length squared, so we can write our area as L squared, and that'll be times phi. And now we can solve for the amount of shear force that's needed. So the shear force, we just multiply by L squared times phi, and this is going to be the shear modulus of brass times the length squared times the angle that we're going to deform it by. And so if we plug all of this in, the shear modulus for brass, if we look that up, it's 0.36 times 10 to the 11th pascals times the length, which is 0.01 meters, and that needs to be squared, times 0.7 degrees, but we need this in radians, so I'm just going to convert it here. You could do it separately. 2 pi radians for every 360 degrees. Okay, and if we plug all of that in, we get 4,400 newtons, or 4.4 kilonewtons. So I hope this gave you a useful introduction into elasticity, Young's modulus, bulk modulus, and shear modulus. And I hope these problems helped you see how these equations are used and how you calculate these properties. And I'll see you in the next video.